Good evening, everyone. Dear students, colleagues, and audience online. Welcome to Professors of XJTLU Public Lecture. 欢迎各位莅临在西普听讲座。I'm Professor Bei Tang from the School of Humanities and Social Sciences. It's my great pleasure to be the academic chair of this lecture series. Professors of XJTLU Public Lecture is our university's signature event for scholarly communication and knowledge dissemination. At XJTLU, we have now more than 50 professors, and we would like to promote our unique research culture through them. This public lecture series will be presented by XJTLU professors from various research fields, showcasing their career-long research, a thorough review of selected research topics, and the latest developments in the field. The lecture series will be offered throughout the academic year to all XJTLU staff and students and the public. Through stimulating presentations using plain language, the professors of XJTLU Public Lecture Series will explain complex research topics and showcase our university's research impact and contribution to our community and the society. Today's lecture is our first lecture in the year of 2025. We are very honored to have Professor Lei Fu as our guest speaker today. Professor Lei Fu is the Executive Dean of the Academy of Pharmacy at XJTLU. Professor Fu received his BSc and MSc degrees in chemistry from Fudan University and his PhD degree in chemistry from Stanford University. He joined Pharmacyclics Inc., California in 1998 as a scientist and then a group leader. He led the drug discovery and development process research on anti-cancer and anti-cardiovascular diseases. In 2006, Professor Fu joined the Shanghai Jiaotong University, leading research that interfaces chemistry and medicine. And in 2021, Professor Lei Fu joined XJTLU's newly established Academy of Pharmacy, leading the strategic establishment of the academy and its curriculum development. Professor Fu has over 80 peer-reviewed publications, mainly in drug discovery. He holds more than 20 US and China patents. Professor Fu also invented two cosmeceutical products containing traditional Chinese medicines and licensed to German companies Henkel and Beiersdorf, respectively. Professor Fu initiated a collaborative research project with Ethiopia Addis Ababa University Center for Innovative Drug Development and Therapeutic Trials for Africa. In today's lecture, Professor Fu will tell us the dark side of oxygen. He will show us what happens when oxygen goes mad, and if oxygen therapy could change the future of medicine. Professor Fu will talk for about 15 minutes, and then we will open the floor for questions and discussions. So without further ado, let's welcome Professor Lei Fu.
Well, thank you. Thank you, Professor Tang, for the introduction. So I'm going to tell you a story about oxygen today. That's the molecule I've been working for about over 30 years of my career. And we've been discovering all kinds of new things, unknowns, throughout the 30 plus years of my research. So let me start it from the beginning. Somewhere around about 35 years ago, I went to California. I went to Stanford University. I went for graduate school. So at the time, every graduate student are required to talk to 10 professors before they join the research group. So I have to talk to every one of them. And I learned from the professors that three molecules are fundamental. They are hydrogen, nitrogen, oxygen, and nitrogen. For those who are chemistry major, probably are familiar with that. Hydrogen, there are two hydrogen atoms linked together through a single bond. Oxygen, on the other hand, a double bond. Nitrogen, triple bond. They contain energy in the chemical bonds. They are very much utilized. They explain almost every single phenomenon in your life, which I'm not going to go through, but I'm going to tell you a little bit about hydrogen. Hydrogen, in fact, is the building block of the universe. 75% of the universe made of hydrogen. And hydrogen is believed to be the first element formed of the Big Bang. And also at the time at Stanford University, there were a lot of research on space, astrophysics, quantum chemistry, advanced materials, and fuel research as well, and also energy. Nitrogen, on the other hand, is essential for life. You probably have already heard about nitrogen cycle. Nitrogen in the air, there are about 78% of the air is nitrogen. So through this so-called nitrogen cycle, the nitrogen is converted by the bacteria into ammonia. So nitrogen has a triple bond. A lot of energy stored in this triple bond. It's being converted to ammonia, very difficult chemistry though, and used by plants. And then the plants absorb the ammonia and as to build protein, amino acids, DNA, and so on, so that these are critical components for growth, right? So, and also then afterwards, the plants were consumed by animals, including us. The plants consumed, when we died, we decomposed, nitrificated, denitrificated, goes back to nitrogen. So the nitrogen goes back to the beginning, and then that's called nitrogen cycle. So everything goes back and being used and comes back. And then the critical part is the bacteria. Oh, by the way, all the cartoons showed in this presentation were generated by ChatGPT, AI, based on the content of my presentation. So it generates by itself, but I provided the prompts for them to generate it. So hydrogen, there were a professor, Digzel, a couple of professors at that time was working on the hydrogen, and one very famous professor, Henry Taube, was working on the nitrogen. There's one thing in common. Professors working on hydrogen and professors working on nitrogen, the research have already got Nobel Prize. So that left me one choice. So I went to Professor Coleman and I said, well, I want to work with you because oxygen seems pretty interesting. There are 4 electrons around and I want to study it. So at the time, he was working on this oxygen for quite a long time. And I said, I know nothing about oxygen, but I want to work on oxygen. It seems very important. So that's how I started. I started with something that kind of out of curiosity, say what's going on with the oxygen. So let me tell you a little bit about oxygen. You probably learned from your high school science that 21% of air is oxygen, right? So there are oxygens around. And you probably didn't know, or you already know, you breathe 16 times per minute. Every one of us. We breathe about 16 times a minute. That counts about 23,000 times a day. If you convert it to oxygen, which is 500 liters of oxygen you take in to your body. If you put it in the content, the bottle is about 380. That means 500 liters of oxygen is 1,500 bottles of air, of oxygen. You breathe in, though. That's a lot of oxygen. And the brain uses about 20% of oxygen, and there's the 80% is for the other use, and I will talk about that. So oxygen seems fascinating. We breathe quite a lot of our oxygen gets into the body, and what's going on afterwards, and then we'll see. So how humans are using oxygen. So we take the oxygen, about 500 liters of oxygen into the lung, right, and diffused to the blood. So the oxygen-rich blood will deliver to the body cells. That causing the so-called cellular respiration, right? So the cells will take care of the oxygen that reaches the cell. And then some actions, for example, muscle contractions, and the brain will use it, right? So, and also I will talk about some metabolism, the cell repairing, and that kind of all activities will use the energy out of that cellular respiration. There's a byproduct, after you use it, the oxygen, there's a byproduct called carbon dioxide. It's a byproduct of the respiration. So it goes back to the lung and exhale it out. So that it keeps the balance the oxygen and versus the CO2. So that's how our body utilizing the oxygen, and when oxygen gets in, 500 liters of oxygen, and it's been utilized, and then exhale the CO2 and keep yourself alive and utilize the whole thing. So I noticed that there are first-year undergraduate students and probably someone who's not familiar with this chemistry. So ask me and raise your hand anytime if you have questions. So then I will answer your questions and then we'll move on. Or we can save the question at the end. Either way will be fine with me. So what happens when the oxygen gets to the cell? So-called cellular respiration reaction. I have to show you a chemical formula. So for those of you who are not familiar with chemistry, but all you need to remember, this C6H12O6 represents the food, the breakdown food. So for example, fruits, vegetable, and some other food. So they all been broken down to something called glucose, so that you can use it. So you eat, you breathe, you get energy. Life is easy, right? So all you need to do is to eat, and you breathe in the oxygen, you get energy, you release the CO2, and you live forever. Life is beautiful. So, so food, air, and energy, that's life, right? So if everything goes well, you're gonna live forever, because to do is eat, breathe, and live. And goes back, and back goes back on. So eating carbohydrates, and that's the whole life cycle when you eat and when you live. Because there are other things, there are other parameters I want to tell you is there are about 37 trillion cells in the body. A lot of cells. There are a lot of things will take care of this reaction, this so-called cellular respiration reaction. I put it in a very simplified way. So if you want to know some details, I can explain to you. But roughly, all these cells, 37 trillion cells, will take care of yourself, and then in the body. So this is pretty much, so far we're talking about good things, right? So you eat foods being broken down to glucose, and then coupled with the oxygen, and then release the carbon dioxide and energy, and you're okay. But there's one slight problem is that you cannot eat all the time. You need somewhere to store the energy, right? So you cannot constantly eat and release the oxygen. So something's called mitochondria. Mitochondria not only helps the reaction, but also there's a mechanism that mitochondria will convert the energy produced from the food to something to store energy to ATP, something like you can consider as a rechargeable battery. So energy produced from the cellular reaction will be stored, most of them will be stored in something called ATP. The energy is there, and it will release when you need it, where you need it. So the energy in the body mostly was stored, coming from your food and then oxygen, will store in something called ATP. And there's a fascinating number. So the number of mitochondria is huge. There are about 100 to 1,000 mitochondria per cell. So remember I said there are about 37 trillion cells. So there are about 37,000 trillion mitochondria in your body. So it's an astonishing number. So the reaction from the previous slide is the food, oxygen, and energy. And this one, if you strip down to a critical thing, is that oxygen being reduced to water, and the energy produced there will be stored in the ATP. And to produce 2 molecules of water, and energy being produced from this reaction will be stored in ATP, most of it. About 34, 37 molecules of ATP. Why do I tell you this? I purposely put a number in front of electrons and in front of protons. For those of you understand the basic chemistry, if you learn chemistry in high school, you know that for a chemical reaction to happen, you need right component. Second, to make a reaction to completion, you need right amount of component, which means no more, no less. Each molecule of oxygen requires 4 electrons. If you don't get 4 electrons, something will go wrong. You need 4 electrons. At the same time, you need 4 protons for this reaction to happen, which means at the same place, you need to have all these 3 components in one place at the same time to have that reaction happen. This is a critical thing. Otherwise, something will go wrong, and I will talk about that. That's the title says, when oxygen goes mad, when oxygen goes out of control. So this is something, if you don't remember anything, remember this equation, which is oxygen plus 4 electron, 4 proton, going to the water and generate about 36 ATPs. So far, I've been talking about the good things. So a person will take the 500 liters of oxygen daily, right? Utilize it, and then get into the blood. It becomes the oxygen-rich blood, and transport to the cell, and where the cell respiration reactions happen. So your food, your broken down food will be converted to carbon dioxide and water. At the same time, energy will generate within the mitochondria. So this is something you need to remember. So this is the first part of it. And I said energy generated from the from this reaction will be stored in the ATP. So ATP in the mitochondria. So the mitochondria helps the conversion of ADP to ATP. If you're not familiar, but only need to remember that energy is in the ATP. It will be released when and where you need it. So this is a critical chemical reaction from oxygen to water and energy stored in ATP. The byproduct of this respiration, the cellular respiration, is the carbon dioxide. So that carbon dioxide gets removed, so that the CO2 and O2, oxygen and carbon dioxide, is balanced. So you don't get much of the CO2 stuck in your body, or you don't get much of you get balanced amount of oxygen and the carbon dioxide. So far I've been telling you a good thing. So how oxygen works in your body. So you take it and it goes back, and then the life goes on forever, right? And there are about 37,000 trillions of mitochondria, or 37 trillions of cells that helps the whole process. If nothing goes wrong, you live forever, 150 years, 200 years, or even 300 years, as was told from the US government. There are 300-year-old men sucking the patients. But anyway, so what if something goes wrong? When oxygen turns against us, remember I talked about this reaction. So the oxygen needs 4 electrons, 4 protons at the same time, and convert it to water within the mitochondria. What if happened if not enough or too much of electrons, protons, or the vice versa? So if it's not in proportionally, so that something is going around here, so that when there's not enough or too much of these things, electrons or protons, then something called free radical, reactive oxygen species, will produced. Here I presented to you something called, probably familiar with, superoxide, right? Hydrogen peroxide, and just to name some of this. So these free radicals will produce if there is an imbalance of the amount of these hydrogen, oxygen, proton, and electrons. That will happen. That does happen in your body. And also, there's also a problem with the mitochondria. Sometimes mitochondria gets defect, or probably most of you know, understand the mitochondria comes from your mother. The DNA is from your mother. So sometimes there are some defects inherited from your mother, or there's something that sometimes there are 37,000 trillion mitochondria. What if something goes wrong? Dysfunctional mitochondria leads to oxidative stress, and then causes the energy depletion, right? You don't get enough energy because there is something dysfunctional. When the mitochondria is dysfunctional, when something is not enough or too much, and this equation is the essential of your life. I said this is the equation of life. So you have to, if you remember not much of the things, so you probably need to remember this equation. That explains a lot of things when you see the disease. So the oxygen, the dysfunctional mitochondria will lead oxidative stress, energy depletion, and I will explain the oxygen stress later. So that will lead to a cellular damage, and potentially there are diseases associated with this mitochondrial dysfunction. So when this happens, so the oxygen obviously is going to go out of control when this happens. And it does happen to everyone, unfortunately. So let me summarize a little bit. So when you breathe the oxygen, I think but this time I have already convinced you that oxygen is essential for life, right? You need oxygen, and this is fundamental for the cellular energy production. And I have been telling you that if there is too much or not enough of oxygen, will create harmful, reactive species, or reactive oxygen species. That's where the problem starts. So our journey, our life, begins with how oxygen powers of life, where at the same time things can go wrong. That's where the disease starts. The dark side of oxygen. So let me tell you a little bit of the bad thing about the oxygen. So the oxidative stress, as I just mentioned at the beginning, previously, is something called the imbalance between the reactive oxygen species produced. At the same time, your body is actually a defensive system, so that it does have something called antioxidants to neutralize it. So when it is out of balance, and that situation is called oxidative stress. And what these things do is that they attack the DNAs, they attack the proteins and lipids. They made it, compromised these DNAs and proteins and lipids. And obviously, if we have it for a long period of time, chronic oxidative species, that will causing the cancer, right? Aging, inflammation, obviously, cardiovascular disease, neurodegenerative disease, and so on. I think we are all familiar with these terms: diabetes, Parkinson's disease, and Alzheimer's disease. So chronically, if these things happen for a long period of time, and then something will go on, will happen, especially these, I think, familiar terms of diseases will happen. And I think ultimately aging is at least at this point, is not as unavoidable. Chronic oxidative stress. So the question is, there's a dark side. Is there any way we can control it, right? So that, as I mentioned at the beginning, that before I talk about the how do we take control of this, and I'll give you an example of the how we use the oxygen. So there's something called cancer, right? So I said chronic oxidative stress were causing the cancer and aging and so on. So the same thing here when cancer happens. So the cancer cells, the oxygen will fuel the tumor progression. So when the cancer cell is something called the cell out of control. So when they're out of control, they need huge amounts of energy. So they consume more oxygen than the normal cells. So they require a lot of the energy to grow, to progress. So at this time, and you can use you're probably familiar with that radiation therapy to utilize the oxygen to destroy the the cancer cells, there are multiple ways. Either you don't give enough oxygen, or you radiate it so that these free radicals will happen locally around the cancer cells, for example, for the solid tumor cells, so that the radical will kill the cancer cells. So that kind of cancer therapies and so on. So there are a lot of applications. There's good things about oxygen and bad things about oxygen. So it's a paradox of oxygen is in the cancer research. There are also so-called the oxygen therapies. Oxygen therapies are usually used for someone who got, for example, brain damage. Sometimes you don't get enough oxygen for a short period of time, so that or stroke. The blood flow gets stopped, so your brain or somewhere you don't get enough oxygen, so that you need the so-called oxygen therapy. One of my students working on at this point about stroke, about how our compounds will help with the stroke patients. And also, there's something about oxygen as well. Oxygen, remember I said when oxygen goes around, there's free radicals and reactive oxygen species happens, so that they damage the dopamine, produce the dopamine producing neurons, so it gets damaged, so that the Parkinson's disease happened. It is believed that Alzheimer's disease are also related to oxygen, reactive oxygen species. The strategy is, at this point, other than the one I'm going to talk about, you give yourself a lot of antioxidants, right? Antioxidants therapies and so on, change your lifestyles. And there are a lot of applications, clinical applications using the oxygen. I just give you some example, which is very much simplified of the utilizing the oxygen. So back to the previous slide, and I said all you need to do is to find something called antioxidants. Antioxidants, it is to neutralize free radicals and prevent the cell damage. The cell damage including DNA damage, DNA, protein, and lipids damage. And also there's good news is your system, your body itself is a defense system. It already has endogenous oxidants. You have it. You don't know, but you do have it in your body. There's SODs, superoxide dismutase, and all kinds of glucosinins. And these are reducing agents, or something called antioxidants, if we call it in general. That helps you to clean up those so-called, or we call it scavenge, the free radicals. What I actually need to mention that, don't think all free radicals are bad. Sometimes free radicals are necessary because they served as some other purpose, which is not the topic of today, but they served as a messenger. They passed the information, and then, but today we're going to just focus on those bad guys. So there are endogenous oxidants to help clean up the free radicals. There are also some other things you can take, for example, vitamin C and vitamin E or any other polyphenols and so on. So all you need to do, you need to take some antioxidants to help you to fight the free radicals that are produced during this, the oxygen reaction, cellular respiration reaction. And also, of course, you can not only you can take these vitamins and so on, so you can specifically design drugs that help defend yourself, that can scavenge the free radicals and so on. So innovative drug, medicines, and I say vitamin C's, including supplements and so on. So these things will help you to fight for the free radicals. Is there any questions so far? All right. So we'll save it for the end. All right. So drug, right? So instead of I'm taking these supplements, and you can get it from market, and we need to discover some drugs that specifically fight for you to fix the problem. Say, for example, diabetes, Parkinson's disease, Alzheimer's disease, obesity, for example. These are all related to the free radical, the reactive oxygen species, called ROS. So before I move on, actually the following slides is my favorite slides. This is always I used either at the beginning to warm up the talk, or in the middle of my talk is to let the audience take a short break. How many pills a person will take in your lifetime? Take a guess. Thousands, okay, a couple of thousands, right? All right. We get another hundreds. You're very kind. Maybe you want to take a guess? Including the supplements, yes.
Supplements 10 each day, then that's...
Okay, very good. Calculated, let's say, if we started from 50, right? 50-year-old, then the rest of 30 years, which is about 100,000. Yeah, we take a lot. We take about 40,000 pills. That's not included into the IVs and so. So if we only count supplements and medicines, we take about 40,000 pills in your lifetime, if in the normal conditions, not including those having some terminal illness and so on. So in general, we take about 40,000 pills, which is about 40 kilograms of the drug. So I see a couple of students from pharmacy, Academy of Pharmacy, and I'm glad to see a couple of students, first-year students, have already made their choice for the Academy of Pharmacy. Welcome. So this is your job, to make a good medicine. Specific, targeted for diseases. Okay, so let's come back. So this is actually very critical. I can tell a lot of stories about this. For example, the quality, right? So the quality of the medicine. This is 40 kilograms of the material. So quality is very important, right? And I can also talk about the brand name versus generic drugs, but I'm gonna just leave this. If you're interested in it, we can talk about it later. So 40 kilograms is quite a lot. Now, how we get it? How do we get these drugs? So this is the slides illustrate the whole process of the drug development. You start from something from the clinical, right? So information will tell you that what's needed, what kind of problems to solve, obesity, cardiovascular, diabetes, and so on. So the scientist here comes up with an idea or something like a target, right? A drug target, a protein, and also something like chemical structure. It comes up with that, and the chemist will make the compound or couple of compounds, and then test it in a test tube. It's called in vitro test, right? Or you can do it in the small animals, some kind of in vivo test. if you get it right, most of the time it's not, and then you go back to square one, right? You do redesign it and you optimize it, or you don't get it good enough activities, and you go back to the structure modification, and you make different drugs, different compounds, and it goes on and on until someday you find it is something that's very useful. And then you move on to you make it, for example, you want to make sure this compound is stable. It can be formulated in a way that either you IV it or you can take orally. That if you take orally, taste is very important, right? So you have to think about taste of that compound, particularly the compound, how stable it is, when it goes through your GI, how much it's going to be absorbed, right? So these things, so-called bioavailability, how much of this drug is going to the bloodstream, and that's later being delivered to the site where needed. So these things will happen, and once you're lucky, and you will end up with something called new investigational new drug, IND, application. So the top part of it is most of the time it's called preclinical studies. So you got the permission for the IND, and then you move on to clinical. So the clinical study will have go through phase 1, 2, and 3, safety, efficacy, and efficacy again in a large pool of patients. So first thing is about the safety. And then if everything goes well, and you get approved, and you get out to the market. Sounds as easy as it says. But unfortunately, things are not that easy. For those actually just join us, the Academy of Pharmacy, welcome. At the same time, let me tell you a little bit about the Academy of Pharmacy. So when you get into this area and you're going to have opportunity to study, for example, drug design, right? AI drug design. Then if you're specifically, you also can study the, medicinal chemistry, organic chemistry. You make the compounds. And these are areas that you need to study in order to complete this top part of the research, right? And biostatistics, whichever programs you select, biostatistics is an important one as well. We have clinical pharmacy, we have regulatory science programs for you. So you can study any of these or all of these, so that you become the experts. You can be part of the drug discovery and development. There's something I didn't tell you, is that the whole process is not as easy as it looks. It takes about 12 years. 12 years is very long, and $1.2 billion to fulfill the whole process. And only 1 out of 10,000 compounds from the beginning to the end will survive. Only 1 out of 10,000 compounds. So this is a long process, but it's very rewarding. And also in the same time, as I said, if you participated in a pharmacy school, Academy of Pharmacy, you will get a chance to study. If you're interested in physics, chemistry, biology, material science, computer science, you will get find your interests around the way. So AI is going to be there. If you're interested in pharmacology, animal study, formulation, if you're interested in biomaterials, and you will find your own the interest here in all the Academy of Pharmacy. And I said this takes a pretty long time, 12 and 15 years, that's traditionally. With the arrival of AI, I was told to mention a little bit about AI. So AI will help. Let's help ourselves to imagine that AI is coming already. AI can help quite a lot. For example, AI can analyze the vast amount of data set so that it's almost impossible for a human to process the whole data set. But now with the AI, you can do it. So it helps accelerate the identification. So because there's a process of the target identification, compound screening, and de novo drug designs. The AI can accelerate this process. And also there's one thing probably some of you already know called machine learning, so that the AI will help to predict the molecular interactions. So when the structure is known. And also, AI can help with, and also in the preclinical testing as well, so that it'll filter out the ineffective or something called toxic. Remember I said some compounds didn't get through it because it's active, but at the same time it's toxic. So it won't go through become the drug. So toxic compounds probably can be screened out by the AI before even going to the human trial, because the AI can learn from the history of the human trials. I can go on and on. AI can help with clinical trials. AI, one of the most important things, AI can repurposing. This is actually, it's going on now. Repurpose the existing drugs for different indication, because it's already being tested. It's safe, right? At least it's safe. The AI can help with repurposing, because there are some indications that get feedback from the physicians, so that you can repurpose your drug for different indication. Sometimes it's previously called off-label use, but with AI, it can help to process the vast amount of the clinical data and repurpose it. And also manufacturing, I don't need to tell you too much about it. So manufacturing and supply chain, so AI can optimize all this manufacturing, supply chain, and so on. And the personalized medicine, that AI can help. So you can imagine that with the impact of AI on pharmaceutical industry, we're expected to reduce from 10 to 15 years of process of a drug discovery and development period to about 5 to 8 years with the help of AI. Hopefully, will also reduce the cost and also the making life-saving treatment more accessible, but getting cheaper and faster to the market. So this is actually probably the end of this talk. Hopefully, if you don't remember anything today, remember this one. This equation with the oxygen needs 4 electrons, 4 protons to produce water within healthy mitochondria. This is my take-home message. And oxygen oxygen can be both sides for your life, give and taker. You need balance in the oxygen. The third one, oxidative stress plays a crucial role in aging, disease, and there are ways to control the oxygen's power safely, right? So I said drugs can help to control the oxygen, and also managing the oxygen wisely is a key for the longevity and the health. If you can manage the oxygen intakes controlled in a controlled way, well, you probably can live longer. Okay, so my final slide is my favorite slide. This is actually so-called Earth at night. All the dots here, the lights represented the human activities. So you can tell more of human activities here, Europe, China, and Asia, and so on. I call it light of life. Whenever there's life, there are diseases, there are diagnoses, there are treatments. Medicine is where the population is. Follow the lights. Congratulate to the undergraduate student who choose the Academy of Pharmacy as your major. And I have the last word for you is because pharmacy rocks. Thank you.
Thank Professor Lifu for such an interesting lecture. We all look forward to a very healthier life. Now we would like to open the floor for questions and discussions. To the audience online, we will also take your questions if you post your questions online, and we will try to get back to you as soon as we can. So for the audience on site, is there any questions or comments? Please just let me know. Wait.
Okay.
The lady there, yeah, thank you.
My question is actually about one of your first slides, which is, thank you. You mentioned that oxygen has not yet won the Nobel Prize, or people studying oxygen. And my question is why? Is it because it's harder to study? Is it because it's not so many people have studied it in the past? What's the difference between that and hydrogen and nitrogen?
Okay. I probably have to go back to why the study of hydrogen gas gets somehow the Nobel Prize, because if you look at the chemistry, this is probably the simplest reaction ever, because there's only the hydrogen atom is the smallest one in a periodic table, and the bond is only one single bond. So basically, people used the quantum mechanics or use the laser to freeze the atom so that it is like becomes too solid a ball to make them to look at the interactions between these two. So that's very early times when the laser is available, so that reaction gets recognized. Nitrogen, on the other hand, 3 triple bond. Nitrogen gets Nobel Prize is because at the time, nitrogen gets the Nobel Prize in 1982 or 86, I forget which one, by giving to Henry Taube. So is that the research is so significant because it answers the question of life. So how nitrogen being broken down to ammonia. 3 triple bond, a triple bond, break a triple bond is very difficult. So that that's why the research gets recognized. Oxygen, on the other hand, that's my own speculation. Oxygen, a lot of people studied oxygen. And a lot of people studied oxygen is because they already know the single bond. They already know the triple bond. So the double bond becomes, to understand the double bond becomes obvious, right? So you can't study the double bond to get the Nobel Prize. Probably is that you need to find some unique application for that. And there are too many. And I think you can probably look in the oxygen studies. Everybody goes, they're related to life, animal, plants, almost everywhere, and you need oxygen. So that's probably my speculation. Yeah.
So I have a question. Basically, what is the function of the mtDNA? And it mainly works on the regression for the MT itself, or deliver the message outside for other parts of the cell. And basically, what's the difference of mtDNA to the nuclear one? And can we isolate it for sequencing so that we can understand its contribution to diseases based on the genetic information? And also you said that the mtDNA is passed from mother to children. So I suppose that in a large scale that we can see there will be a more similar disease pattern between mother and the children compared to father and the children. So if we can have a larger population, then we can actually calculate the magnitude of contribution of this in terms of many different disease types. Thank you.
That's a very good question. So you got actually two questions, right? So let me answer your second question first. The best person to answer your question is Professor Chow here. It's true. The DNA of mitochondria passes from mother to the offsprings. So any defects in the mother's mitochondrial DNA will pass it to the next generation. And it's true, but not always expressed. Depends on how much is mutant. Sometimes, I think it's about, if it's below 15%, it doesn't even care. That's okay. So if there's a 15% defect, I remember it's about 15%, roughly. So you will not show. It will not, most of the time you wouldn't even notice. Now back to your first question. It's true that you may get, there's a possibility you inherit it from your mother and pass it on to the next generation. Back to your first question, yes, you can do a sequencing thing. You can isolate it. That's what we're doing. So we treated our compounds. For example, we intervened with our compounds so that we will see how mitochondria change it. So we can sequence it. There's a lot of work, and one of my PhD students is still working on it. So we give it to the animal for a long period, for extended period of time, and then see the change by taking the DNA sequencing, so that we will figure it out. So what our compound will actually functions in a way, or one way or the other. That's how we actually discover the drugs, specifically for specific disease. That's a good idea. Thank you. Here we go.
Yeah, so what my question is, we always talking about the shortage of oxygen radicals in our body. But if I imagine that if there are some benefits of these oxygen radicals that we can use to degrade some other invaders in our body, is that possible?
Very good question.
Is there any phenomenon in nature that shows this?
Yes, we are actually probably missed one of the slides, the therapy. So the therapy, for example, I take the cancer as one example. For the cancer cells, it takes much more energy and nutrients than the normal cells, right? So you need to produce a lot of energy in order to feed that. So there's a therapy that you cut down the oxygen, so that you cut down the overall, but you make the cancer cells uncomfortable and then die. That's one thing. The other thing is you can use the radiation For example, when I used to work for a company in pharmaceutics in California, so we made a compound so that it is radiation sensitive. So when you shine the X-ray on it, so it produced locally the free radicals to kill the cancer cells. So this is another way of using the free radicals. There are good news and the bad news, and it's true. So sometimes you need to clean up all the free radicals when it's harmful, but also at the same time, free radicals can be a good thing to help, and also free radicals can be a messenger as well to pass the information around. Very good question. Agreement, that's good. Yeah.
Thank you very much, Professor Fu. That was a fantastic talk. So I'm just very curious that in the field of mitochondrial targeting drugs, what would be the next big target or the next big drug that could have really impactful changes to the field?
Okay, remember I said there are about 37 trillion of cells, and there are probably 37,000 trillions of mitochondria. So mitochondria is everywhere. So once you attacked or targeted mitochondria, it could be everywhere. This is bad news. But good news is there might be a lot of applications because it's probably on the very top of the chain, so that a lot of disease, in fact, it's true. A lot of disease, most of, actually, I wouldn't say a lot of, it's actually, I wouldn't say all, but most disease are mitochondria related. So we need to have not only mitochondria specific, hopefully our drug could be organ specific. So that's probably the next thing. So that I think we're working on not only some compounds that one of my students also are working on, not only mitochondria specific, it's cancer cell specific. So it gets to only the cancer cell instead of the normal cells, so that it helps may become the next generation of cancer therapy targets. You're right. My prediction is as good as yours, but I mean, this is because the mitochondria is upstream and they're going down, and you can do a lot of things are related, right? Inflammation. We have students working on ALS. We work on the diabetes, chronic disease. These are all mitochondria related. The only thing is how we going to deliver our drug in terms of organ specific is a challenge. This is very, very difficult. And you can wipe out all the mitochondria, but you wipe out the whole thing. So mitochondria targeted therapy is difficult. It has to be organ specific. Like ADCs. ADCs can help. Yep.
Okay, let's thank Professor Lei Fu again for today's lecture.
Thank you.
And we wish everyone have a healthy life, and thanks to all the amazing work of the past generations, the current generation, and the future generation researchers in pharmacy. Thank you, everyone.
Thank you.